Okay, so with any tool, you're going to have parts that you're making. That's the purpose of a tool. A tool is something that helps you manufacture something else. And, in the first day of class, we kind of talked about, what is manufacturing, and you have a general idea of that. And, there are aspects to manufacturing of quality and all that goes into quality, and there are all kinds of aspects. But when it comes to tools, you're going to be trying to make something. And the thing that you're going to make, one of the main things you're going to want to do is you're going to want to be able to make the thing with the tool, use the right tool for the job. That's pretty obvious. But the main objective is to make the part as cheaply as possible while maintaining what the original spec was. So, if you are trying to make 100 parts and the total cost of those parts is $1,000 and you can make $10,000 on those 100 parts, if your tools cost more than what you're going to make on the parts, then you're not going to make a profit. So, that's just a basic thing. So where this comes into play, and that seems obvious, a lot of these things, they seem obvious on their face, but, if you have some CNC machine that you want to buy and it's a really, really cool, expensive CNC machine, and let's say it costs, $600,000 or something like that. If you don't have enough jobs to pay for that CNC machine, it's not going to work very well, right? There are a lot of reasons why small machine shops come into online and maybe they buy really good equipment. They can take on a wide range of work, but the cost of their tools essentially just outstrips how much they can make on the parts they're making with those tools. So that's a very important thing to understand. And everyone is bound by this. So, whenever you buy something, it's always going to take into account how much do the tools cost. And that's a lot of how you select how you're going to make something. And also affects how you're going to design a thing to be made. Okay. The other thing is you're going to want to be able to make parts as quickly as possible. So, and when I say within the given rate specified, at least, what I mean by that is if you need to make 100 parts a day, you want to make 100 parts a day. You don't want to make 99, and you don't even want to make 101 parts. You want to make 100 parts. And ideally, you want to do that with the least amount of work possible, with the smallest amount of tooling. Another aspect is you always want to design a tool that's going to ideally provide the most consistency, okay, or the most stable process. So, for example, if you have a nice CNC machine, everything's very rigid, the tooling is rigid, the fixtures are rigid, you can get good repeatability out of it. And a CNC machine, they have tool changers, so if you have a CNC machine, maybe you have one CNC, and that equals, 10 tools. We could have end mills and drills, and let's say we have 10 drill presses. And then, if we have one CNC and that one CNC has 10 tools in it, and that equals 10 drill presses, maybe we can make a part where we put it in the CNC one time and we do 10 operations to it. And if we didn't have the CNC machine and we were using drill presses, maybe we'd have to move it between 10 drill presses. And so that moving of the part from drill press to drill press might cause inconsistency in the parts. Okay, that's just a made-up example, but that's a way to think about it. So you want to have consistency in your parts, and you want to have stability. Think about this in a different way. If you're playing golf or something, if you could make your swing identical, swing to swing to swing, you could play a perfect golf game. But you're trying to get consistent. That's difficult to do, and that's with whatever you do. So with machining or manufacturing, part to part to part, you want to have the same process, and you want it to be stable. Even if it's not correct, if it's stable and if it's consistent, you can control it. You can adjust it to get it where you need to be. Okay. And another thing to consider is that you want tools that are safe and easy to operate. So basic reasons for that are you want them to be safe, right? You want to go to work with 10 fingers, you want to come home with 10 fingers, kind of an idea, right? So you don't want to get hurt at work. No one should be getting hurt at work. That's not how how good businesses run. So everything needs to be safe, okay? And they should be easy to operate. Part of that is the easier things are to operate, you don't need as highly skilled workers to operate them. That's part of the aspect. But then the other thing is the harder they are to operate, the higher probability of a mistake being made, even by a highly skilled worker. So they need to be safe and easy to operate. And also, I would argue that you want to make them environmentally friendly. So, if you can make some part using a process that requires something that's relatively benign and safe for the environment, and you can do the same thing with some chemical that's very hard to dispose of safely, probably should use the safer thing. So that's a big thing that's kind of being looked at more now than maybe it used to be. And I would say it's a good thing that environmentally friendly tools and designs are being considered, because we only get one planet, so might want to take care of that planet. We all live here. So that's an important aspect as well. And there are many other aspects in some of these topics, whether we're talking about drill presses or jigs or fixtures or what have you, they'll come up again and again and again, kind of similarly. Okay, so, but these are some things, the cost of the venture, needs to be, less than, the cost of, or what you're going to bring in, right? So if you spend $2 million to make, $1 million, it's not going to work very well, right? You're gonna quickly run out of money. So that needs to happen, and you need to be able to make them on time, right? If you say, I can make that part for you, no problem, I can do it cheaply enough, and you need it in 10 months, I'll have it to you in 20 months, you're probably not going to get the job, right? You need to do it on time. And again, stability in a tool and repeatability, even if the tool's not kind of calibrated in where you want it, as long as it's consistent, you can get it there, but it needs to be consistent. Okay. So also, how does the operator work with the process? Is the operator, is this something that the operator is easy to interact with? That's something we'll talk about a lot, because an operator being able to interact with something is paramount. Simple things like doing the same movement over and over and over can really cause a lot of harm to a person. So having something be ergonomic, as simple as that may sound, it's actually very significant. So motion injuries at work are probably some of the most common injuries. Somebody getting their hand cut off in a machine, that happens, and that's really sad when it does. But usually what happens is they don't get their wrist cut, they get carpal tunnel in their wrist from doing the same movement over and over and over again. So that's something that needs to be thought of, because for most things that have to be made in real life, people are going to be interacting with them. So they need to be made ergonomic. And that's something that's been probably not on the forefront of people's minds 50 years ago, but it certainly is now. So whenever you make anything, you're going to have to accommodate that. And if you even look at, simple hand tools, not just CNC machines or big machines, but if you look at simple tools, if you buy a hammer, if you go to a big box store and you buy a hammer and you look at the section with all the hammers, and look at how many hammers there are, right? And they have all different kinds and types, and most of them are going to claim at least to be ergonomic in some way, and most of them are. Okay, so that's the same with any sort of manufacturing tools. You want them to be ergonomic. So it could be as simple as you have two different operators, first shift, second shift. First shift operator is 5'5", and the second shift operator is 6'5". So the second shift operator, their head's tilted down to see the work, and the first shift operator, their head's tilted back, and maybe you want their head to be in a more neutral orientation. So the workstation that they're at might have to change its elevation and orientation to accommodate that person. That's a really common thing. So not everything can be adjusted, but as much as possible, things should be adjusted to make it easy for the person to do the work. And as engineers, you'll get to hopefully have input in that. So also, general design objective is the fixture easily secured in the machine. So that seems obvious, but that always has to happen somehow, because most of these machines, if you think about something like a CNC machine, And most of you have seen them, and for those of you who haven't, we will be going down in the lab, hopefully, and looking at the machine that we have. You'll see that the CNC machine is really a multi-purpose tool. It can handle a significant number of different tools to do different jobs. And the workpiece, you'll see the table. When there's nothing on the table, it's just a blank table. And it's not the kind of thing where you can just put the workpiece down. You have to hold on to it, right, to resist the forces input into the workpiece by the cutting tool. So the fixture and the tool need to be secured in the machine, and they need to be done so easily, right? You could take a part and you could weld it to the table, and then you could machine it, but now how do you get it off of the table, right? So that would be a ridiculous way to do it, would be to weld it down. But you need some way to fixture it. So is it easy, and is it actually secured? So in those tables, you'll see the keyways. And we'll show videos that show that, and we'll actually look at it in the physical machine. Simple things like, do the fixture keyways match the machine keyways? I have seen fixtures that were built that were very, very expensive, tens of thousands of dollars, and took a lot of time to develop. And then when they arrive, they don't fit in the machine because they don't match the keyway when they were intended to. So, simple things usually defeat larger things. So that's even something you need to think of. So how does the machine that you're going to use, how do you need to adapt your tools to work with that machine? That's a real basic thing, but it's something to think about. And if you're new to machining, always be thinking of that. Okay, so I have this thing I'm going to work on, this part, and I have this fixture that I'm going to hold the part in. How am I going to attach that to the machine, right? So if you're using a hand drill and you're in your backyard and you're making a chicken coop, and you're drilling a hole through a 2x4, you just maybe hold the 2x4 in your hand or step on it, and then you push the drill through it. Well, when you're machining something with a big machine, that's not the case. You're not going to hold on to the workpiece. You're going to need something to clamp it and hold it down to the machine, and then the machine's going to work on the part. So you need to think of that. And then, as always, the repeatability and reproducibility of the process are paramount. So you need to be able to do this job you're doing, and maybe you have to make 100 parts a day. So you want all 100 of those parts to be able to be loaded and worked on and come out of the machine, ideally in the same exact way. Now we know that that's not going to happen. We know that there is going to be some small error in some way. And in some of your other classes, some of you have been through with me or the other professor in manufacturing engineering, you'll hear us talk about tolerance stack, and you'll take GD&T class where you'll learn all about tolerances and how they're involved. But tolerance is a fact of life, right? So we can't make things that are perfect. But we want to try to minimize the variation as much as possible. And then also a real simple thing, which I think I mentioned already in class, are all the sharp edges and burrs removed. That in of itself, when you're making things, is a huge deal. Because the context of this class is we're making parts. Most of them are going to be made out of metal. Some of them are going to be made out of plastic or maybe carbon fiber or something like that. And in a lot of these processes, the clearly defined edges in the design aren't so clearly defined when we make it. So we get some sort of part, and we make something, and let's say we have some sort of little curve on it like this, and then you get some sort of little like jaggedy edge there, or you have some plate, and then you have a hole in it, and after you drill the hole, you get some like raised burr that kind of hangs out from it. Okay, well, how do you clean that up? Because the design calls out this nice, clean, perfect hole, but in fact, you have some sort of little flake of metal hanging in there, and maybe it's attached really well, and you can't just hit it with compressed air and knock it out of the way, right? So how do you get rid of that little teeny burr there? And what do you do to mitigate that? So one of the ways you can do that is there are certain tools that are made. One of them is called an easy burr, and an easy burr is a pretty useful little tool. And let's see if we can see that here.
Manufacturing the finest handcrafted deburring and chamfering tools on the market. This same commitment and dedication has led to Easy Burr's numerous active patents. illustrating a constant innovation that allows us to provide you the quickest, most effective, and most reliable product available. Welcome to Easy Burr Tool Company. The educated
Easy Burr is not the only tool company that makes a burr removal tool, but they are one that I have personal use using. I've used these firsthand, ordered them and used them, and they work quite well. The concept is the same, but for those of you who don't know a lot about machining quite yet, this is a very common problem: is how do we remove burrs? The best way is to design the burrs out, but sometimes it's very difficult to do. So you make the burr, and really the burr is a type of defect, and we've talked about that in our quality class. For those of you who have talked or been through that class and heard me or the manufacturing professor talk about this, a burr is really a defect. It's something that you make that you don't want, and it's better if you don't make it in the first place. But occasionally, you cannot get around it, and this is a way to eliminate it after the fact.
The consumer expects and demands full quality control on every product purchased.
So this is the actual tool itself.
At Easy Burr Tool Company, we share that expectation.
So these holes that have been machined may have some sort of burr around the lip of the hole, and somewhere right in this area right here, you're gonna see some sort of.
All of our tools are.
Let's see here.
All of our tools are finished in-house at the heart of our operations under the strict guidelines of ISO 9000. During the first for easy, they are easy to maintain, and setup is quick and straightforward. From transfer lines.
So essentially you have this part and you have holes in it, and this little tool goes back into the hole. It doesn't create the hole, but it goes back into the hole.
And CNC
the little tiny piece here that sticks out, this little blade, has a cutting edge, and you'll see here on these holes there's a nice raised burr. You can see where on the edge of that hole there's kind of like a little raised metal area, and when the tool comes back through, it will eliminate that. See, it just chopped it off.
Our product line consists of 3 main series of tools. The tool arbor, as it passes through the applique flexible blade that after cutting will.
So there's the blade, and the blade can actually spring load push back inside of the tool body as it passes through the part, and it can do that in both directions.
Into the tool arbor as it passes through the application, emerging on the other side of the hole and continuing burr removal.
And obviously when the part's being deburred, this tool is spinning, it's rotating, right? So it's cutting that burr
Additionally,
away. Okay, and you can watch the rest of this video. It's actually a really good video, but there you see, this is a perfect example. Those are burrs left over from a drilling operation, and they're hanging all over there. That's bad. You don't want that. And watch as this tool goes through, it will just cut them off nicely. Okay. And your book talks about burr removal, I believe, and what kind of a big business it is. And it's not a business in the sense of, it's something that you want to do. It's something that you have to do. But it's essentially a defect. So, and then also another thing to consider is vibration is a big problem. Whenever you have things moving, you can get some sort of vibration. And a general thing to have in the back of your mind whenever you're doing anything is, can vibration from what's going on cause the tool or the workpiece to loosen while in use? Because remember, the context of this class in general tool design is everything from simple jigs to CNC machines, and big presses and injection molded parts and everything in between. And, a lot of things have to be bolted or fastened together. In a lot of cases, those things can come back apart, maybe in a way you don't want them to. So that's something you really want to consider while you're designing your tools. Okay, another thing to consider is, or another list of things to consider is the tool self-cleaning. Okay, so a simple way to think about this is, if you have some sort of fixture, and I'm just going to draw a real simple fixture here. So this is a fixture, and here's some plate, and let's say we bolt our workpiece down, and this is our workpiece here. WP is our workpiece. And then we have some sort of tool coming down here. It's some sort of drill, and that's on some CNC machine. It's coming up like this, and here's our little drill with little flutes, and it's going to drill a hole in here. And let's say we have some sort of coolant nozzles that are coming down, and they're spraying coolant all over here. This design right here is going to make so that this area is going to get full of coolant, right? And full of chips, and they're going to flood in this area. When you go to take that piece out, that work piece, here you have your work piece now, and it's got a nice hole in the top because you machined it. Okay. Now you have this workpiece, it's out, you machine a hole in the top, and you go to put the new workpiece in over here, and now you go to put that in there, and you can't locate it correctly because there's coolant and chips in here, right? And so that's going to cause a problem. So that the part needs to be self-cleaning if possible, and the chips and the coolant must self-evacuate. So a better way to do this would be if you had some sort of fixture that was maybe shaped like this, and you had the same workpiece, and the workpiece was maybe sitting on the top here, like this. And there's our workpiece. And that way, when the drill is coming down to drill in here, all the coolant from the coolant lines that are getting flooded on this, it's just going to roll down the sides, right? And it's going to kind of be self-cleaning, okay? In a lot of the lean manufacturing, they say Mount Fuji. So think of it like Mount Fuji, and I think that's how you spell Fuji, right? F-U-J-I. So Mount Fuji. So basically, you introduce some sort of, you create chips, or you introduce some sort of coolant or something, and it just kind of rolls down the mountain, and it cleans itself off, right? So your general, you don't want some shape like this where stuff can fill into here. You want a shape like this where stuff can just roll off. Okay, does that make sense? So that seems like a basic thing, but you would be shocked at how many tools have little pockets or areas that are not easy to clean. And if you don't do this kind of a design, and you do this kind of a design, you're going to spend a lot of time cleaning the pocket that catches all the chips. And any of that time is really waste. It's not value added, okay? And that non-value added time has to be paid for. The customer is going to pay for that, but the customer doesn't want to pay for non-value added activity. Okay, either that or you're going to pay for it, and it's going to eat into your profit margin. So you don't want to do that. Another thing is, do the chips and the coolant hit the operator during the operation? Do they do that? They shouldn't, right? The operator should be safe when they're running the machine. Most shop floors you go to, you're going to want to wear, at a minimum, long pants and long sleeves and safety glasses. But sometimes, you need to wear more PPE than that. And that's something that you're going to want to be aware of, okay, is making it so the coolant and chips can't hit the operator. Also, loose parts of the fixture need to be secured or cabled. Sometimes you'll have a fixture and you'll have some sort of, you have some sort of tool. Maybe it's like one of those wrenches. It's like a T-handle like this, and it's got some little, handle, and then you use it to turn a nut or a bolt, and they'll kind of like stick it in a fixture or something, and it just kind of floats around in there. Avoid doing that. So you don't want anything that's loose or moving around. If it's going to be, it needs to be secured at the very least in some way, but better to just not have them there. And then also, can you unload and load? This goes back to, is it ergonomic? So ideally you have something that's self-loading, but that's not always possible. So think about it. If I had some sort of basket, right? And let's say, let me get rid of some of this stuff. Let's say I had a thing that looked like this, and let's say it was a tube, and the tube goes to some reservoir, and I want to put little marbles in it. And here are my marbles. And I want to drop the marbles into the tube, and then the marbles fall into the tube, and they fall down like this, and then I have marbles in here. Okay, and if I drop one and it rolls away, then I've lost my marbles. Okay, but that's something I can do that. But I got to pick each one, and then I got to place it I got to take this and I got to place it right over here and then drop it in the tube. And that's not easy because I have to line that marble up with that tube. That's not easy. If I had something shaped like this, where I had some sort of, funnel, this is going to be way easier for me to load. I'm not going to lose my marbles doing this, right? Okay, because they're just going to fall right down here, and I'm going to have my marbles. Okay, so I can drop my marble anywhere. I can throw it halfway across the room, and it's going to fit into there. Okay, so this is a good one. Good. This one is bad. Okay, from the standpoint of, is it easy for me to load and unload? Now that's kind of a ridiculous, example, but again, it proves a point. And sometimes you'll see tools that are very difficult to load. The setup time is usually what takes so much time. So you want to avoid your setup time. You want to make tools that are easy to load or fixtures that are easy to load. That's what you should aim for. So ideally the marbles come in a big box, and then we just cut the box open, and then they all roll down a chute, and then they fall down into here. We don't want to have to pay a skilled worker to wear cut-proof gloves and just pick one marble at a time and carefully hold them over then to this tube and risk cutting their fingers or dropping their marbles and losing their marbles. Okay, I want to make it as easy as possible. Okay, and then also, since this book talks a good deal about jigs, and some of them are handheld, and there are plenty of handheld jigs that are made, you need to have enough leverage. So motion injury can result if you don't have enough leverage for things. So anything you do, you should have enough mechanical advantage, so you're not relying on someone's strength to be repeatable, to do it as much as possible. So, and you should try to do something automatically or automate it if at all possible. That's better, having a robot to do a repeatable task. And I'm not saying an actual robot. Sometimes it's as simple as just thinking of a clever fixture so that small amount of pressure can be applied, maybe, or use some sort of automatic air or hydraulic cylinder to actuate something so a human doesn't have to. A human just has to push a button, and then something happens instead of a human grabbing some sort of lever and cranking on it real hard. So that's something that needs to be looked at. And then another thing is to make the tool easy to repair if it's damaged or worn out. So sometimes tools are made as one piece, where if one small spot wears out, the whole tool is worn out. And an example of that, I could have some sort of tool where I essentially, let's see here, I got some sort of plate, and then let's say I have some sort of rest buttons on it, and I have some part that I lay on them, and then I work on the part. Well, if this is all one piece, if this whole thing is one piece, and one of these rest buttons gets damaged for some reason, now I gotta throw this whole thing out and start over. Okay, but if instead I make it so that those rest buttons are separate pieces, and then those pieces fit maybe into holes in the part, or I can take them in and out. If one of them gets damaged, I just throw this out and I don't throw the whole thing out. Okay, so the good news here is if you make something that's in multiple pieces, you can just usually throw out or take apart and throw out the one piece that you don't want to use anymore, that's worn out. The bad news is you have to worry about things like it coming apart, and usually it's more complicated design. Not always, sometimes it is. So there's good and bad to both, but usually you should make it so it's easy to repair, because the worst thing in the world is taking time to work on something that could be made real simple. And if possible, you should make the tool self-repairing. So we'll talk about that more in class. It's not easy to do, and it lends, there are certain situations where you can do it, but you can have things where a locating clamp is designed so that as it wears, it doesn't matter how much it wears, it will still be able to clamp, and things like that. Sometimes if you have a sort of a clamp set up with a very limited stroke length, when the end effector that's attached to that stroke length gets worn, now the stroke can't extend any further to clamp, and you maybe have loose parts. You want to make something so that it could accommodate a wear situation, and that's what I mean by self-repairing. Nothing is self-repairing but you want something that will kind of adjust as much as possible automatically as wear occurs within reason, if possible. Not always is that possible, but if it can be done, it should be done, because wearing out is a fact of life. Eventually we even wear out, but you want to try to extend that in most cases as much as you possibly can. That would go for your tools as well. So also, a designer is going to need to know about all the tools that are going to be used or could be used to make the parts that they're tasked with making. So if you work at a company and you're making wire, or you're making gauges for aerospace work, you're making gauges for some sort of gear component or who knows what, you need, as the tool designer or the manufacturing engineer, you're going to need to know the details of all the tools that you could have on hand and could use to make or in some way fabricate pieces of that part you're working on. In general, the tools that you'll see over and over again are contained somewhere in this book. So again, if you read this book cover to cover, you're going to have a great handle on things. And it's pretty wide range. A good manufacturing engineer, a good tool designer is going to have to know a lot of little details about a lot of equipment. And just this list here doesn't cover everything, but it covers a good amount. A lot of parts here are made in this area through these methods. So, whether it's the typical mill lathe, or, there's wire EDM, there are bulk forming processes, there are details to all of them. You're going to need to know the general idea behind a lot of these. Nowadays, there's a lot of 3D printing, which is still rather expensive, and for rather, I would say, low volume items. Most things are made in more the traditional subtractive way, and they will probably be for some time, just due to cost constraints and throughput. So, but it's important to know about the newer technology coming along as well, and the old technology. So, between jigs and fixtures, and also gauges on how to measure parts. A lot of parts are measured not with, more robotic CNC or CMM type machines. They're going to be made with hard gauges that are essentially metal gauges that are fixed, that are made to measure a very specific part in a very specific way. That is a whole field unto itself, and you're going to need to know at least something about them. And also, metallurgy is something that you'd need to know in general, and that's something that would be very... And also, you're going to have to understand whatever CAD and file management your system or whatever your company uses. That's important. And what is your realm at your employer? So, if you get hired to make fixtures, that's what you're doing. But you should at the very least have a basic understanding of the inner workings of all these things, and that'll make you a better engineer and better tool designer in general. So also, with a lot of the engineering problems that you'll face, the design process is as follows. And this goes for, you see this in your math classes, in your statics classes, your mechanics classes, your physics classes. You need to have a statement of the problem and analyze the requirements. A little different might be develop initial ideas. Sometimes with tool design, you have to get pretty creative. So if you think about fixturing, for example, if you have a new, unique part, you're going to likely need new, unique tooling. And also remember, you're always bound by time and cost. So you can't take forever and you can't spend as much as you want. You usually have a fixed budget of time and money. And oftentimes there are multiple alternatives, and usually those come into play in the sense of lead times and quantities. So if you're going to do a quantity of parts that is maybe smaller and you want to get it up and running quickly, you might machine something, and maybe long term you would cast it. But maybe the material and the tooling for the casting would take longer. So you'd have a short-term solution, and as the project grows, maybe you roll it into a long-term solution or something like that. And then finalize the design. And the parallel paths part comes from, if you have multiple different avenues of manufacture, the design is going to probably be likely different. So the way you would design a part that's machined out of a solid billet, you may do it differently if you're going to do it near nut shape out of a casting or a MIM part or something like that. So it doesn't mean it's a different part in the sense of the way the specifications come to be met, could be the same, but the actual part itself is slightly different based on the manufacturing method. And then the economics of the design. So economic proof is always going to be required. So in general, unless it's your own money and you're getting to spend it however you want, and even then you should still adhere to this. But generally, you're not going to be spending your own money. You're going to be spending someone else's money, and they're going to be, concerned about how you're going to spend that. So I just said that MIM limitation is a good example because sometimes, if you're going to make a part, you might look at a part, you might say, wow, the best way for this is a near net shape type process. But it may be that you're only going to do a couple of them, or you're just experimenting with them to check for this smaller parts function in a larger assembly or something to that effect. So you're going to have to do the math and figure out, and we'll talk about that later, about how you actually calculate whether that makes sense. So, what it boils down to, if you're selling lemonade for more than it costs to make the lemonade, then you're theoretically profiting there. But if you have your little lemonade stand and you're selling it for less than it costs you to make it, eventually you're going to run out of money and you're going to have to shut down. So the economics of the design is always going to be a big deal. And, this is a good take, I think. Simple is usually cheaper and better cost-wise. So the simple design is not always better. Some designs have to be complicated. That's just the nature of some things. But you'll get a feel for it in a sense of, as you're looking at different tools and tooling and methods, usually the simple method ends up winning out. Because simple usually means less steps. And in less steps, there are usually less opportunities for error. So, there are plenty of processes I've seen that require, let's say 15 steps. And usually as a result of digging in and figuring out how can we make this cheaper, we don't usually come away with 30 steps. Usually it's a minimization process. So, it used to take us 15 steps and now we get it down to 8 steps, and that's better and cheaper because we use less tooling, takes less time, and there's less opportunity for error. Usually those go hand in hand. Not always, I'm sure there's a counterexample, but that's a general rule. A counterexample for that might be if you have some process where you just hold on to a part and you put it in your 5 or 6 axis machine, some real fancy machine, and you machine it down. Maybe in some ways that's theoretically simple versus having a whole bunch of machines where you break the process up. But it may actually be overall cheaper to use a bunch of cheaper machines, even though you're breaking the process up and coming up with some creative fixturing from a standpoint of throughput and durability of the and stability of the system. So, you have to kind of slice it and figure out how is this going to work out economically. And almost always you want to use any preformed materials. So there's the concept of COTS, commercial off the shelf. That's something you always want to do. And when I say don't be a newbie on simple materials, if things come, if plates, for example, of metal come in, 1/2 inch, 1/4 inch, 5/8, whatever even sizes, you want to try to pick sizes that you can use that are those even easy sizes to get. So, you're not going to go and make your own screws and nuts and bolts unless they're very warranted. You're going to try to buy those, right? So you want to stick to what you're good at doing. So you're going to want to use commercial materials, pre-made materials whenever possible. So it's a lot more simple to go and, go to MSC or Carlane or somewhere and buy the bits they have instead of trying to make them. You probably, if you're making something complicated, you probably can make all those things, but it's just not worth your time to do it. So that's, that the preformed and the pre-manufactured tool components are kind of go hand in hand. And then again, always the theme of removing unnecessary operations. So it depends. Some reasons, there are reasons not to combine tools. If you're trying to meet production requirements and you need to, alter tack times, so you need to, remove operations from an area and put them into another area or another machine per se. But in general, you're going to want to combine things. Now, there is a catch. When you combine tools, now you may in some way lose flexibility. So if you have some sort of drill mill or drill reamer in one, maybe you don't get the option now to drill the hole, and then for some sizes we ream with this and some others we ream with this. Now you're locked into that one size. So that's usually every time you combine things down, you lose a little flexibility. But you have to use good wisdom and judgment and decide whether that makes sense for your process. Oftentimes it ends up being a help because it usually saves time, and remember, time is your most precious resource. You cannot get it back. So, and also in general, you're going to want to automate when possible. Automate does not always mean also, including robots, although sometimes it does. Automate just means making things happen without having to intentionally do them. So combining tools, in a sense, is automating a process. You're drilling, and then you're reaming, and then you're burnishing. You had to change tools. You had to load the tools into the machine. Someone has to set the tools. You had to source the tools and stock them and all these things. If you combine it into one tool that does it all in one hit, now you've effectively automated all those other processes in a sense. So you should always be thinking that way. How can we automate it? You don't want to do things over and over and over. And if you take my other classes or the manufacturing engineering professor's other classes, you're going to see that theme come up. Even if you're doing solid modeling, you don't want to be doing the same operation again and again. Sometimes you have to, but oftentimes you find if you're doing that, that means there's opportunity to automate, and usually automation is a good thing. And then the cost of the design, a general rule is going to be the lot size times cost per part. At a minimum, needs to equal the tool cost times the labor rate. So that's just general rule of thumb there. And your break point is essentially, your tool cost divided by the delta between the cost of the part with and without the tool will tell you how many parts you need to at least pay for that one tool. So, if you're, let's say in this example, where we have this simple 40 cent to 20 cent delta, we come up with 750 parts. If you only had an order for, now these numbers are obviously really low. $150 fixture is pretty cheap. 40 cent part is really cheap. But the idea is that if we were only going to make 10 parts, and we said, well, we can reduce the cost of the part by half, we just have to spend, $150 in this tool, then we've already gone over what we ever hoped to make. So, we have to make enough parts. If we're going to make 1 billion of these parts, well, then we wouldn't even think about it, right? We would easily spend that money because it would pay for itself extraordinarily quickly in the process. So these are just good general rules of thumb in how you should begin to think about, do I do this thing? And then the cost of the design. So the lot size will drive the process more than the actual engineered tool solution. That's usually true. So, you can come up with a really, really cool design for just about everything. But if it's not economical and that if it doesn't pay for itself, it's not going to really, really happen. So, I think I have one example in this course of a part where a pretty complicated casting process was developed for only a handful of parts, and it was for a NASA program back in, I think it was somewhere in the era of the 60s or 70s. That's a pretty specialized case. In general, you're going to look at how many you're going to make, and that's what you're going to do. So if you're going to come up with some near net shape process, casting or mimming or something along those lines, you're probably going to need to make enough to make it worth your while, because you're going to have a lot invested into tooling. And in general, as in a business, engineers should be involved with forecasting and future demand in the sense of, how much does this stuff cost to do. So it doesn't mean that, they'll be calling the shots necessarily, but an engineer should and likely will be at least involved in trying to help figure out, okay, if this is what we have for demand, or this is what we think we're going to need, how much is it going to cost for us to get there? So, if we have new demand or we lack demand in the future, what can we do with what we have to still make it work? And most companies have a specific way to do that. and they'll have something, especially if you're joining a company, that's been around for, however long, unless it's a startup kind of environment. They've obviously, hopefully, been in the business of making money, and they've come to this decision before, or this, this fork in the road kind of an idea, and they've had to make a decision, and they should have tools available to them to kind of help them figure that out. And you'll have to learn their process, but it'll be something along these lines. I mean, it's not always a rocket science type thing. It's just, how long is it going to take, and how much is it going to cost, and how much does it hurt the bottom line, essentially. We can't spend more to make something in a really cool way if we're going to lose our shirts doing it, kind of a thing. And then tooling drawings. So usually you're going to use an ANSI standard in any of your CAD classes that you use, or any of the drafting that you've done. There's really going to be a lot of this is covered. This is a tool design class, so we're just going to kind of go over this briefly. You're going to want to make your prints in the way your company is going to want to see them. So, if you're in the United States, you're probably going to use the ANSI standard. So, and also you're going to need, if you have kind of an internal, method where you're making, especially if you're the original equipment manufacturer, you're going to want to dimension and make parts with the capabilities of whoever or however you're making it in mind. So you're not going to want to make it, in a way that the general understanding doesn't recognize. Okay. And you'll have to figure that out when you get to wherever you get to. But let's say you work at a place and you make fixtures for parts that are made on mills and lathes, and you have some tool makers who are running, knee mills and that sort of thing. Then maybe you have a wire ADM here or there. You're going to see dimensions that are somewhere in the thousandths to the tens of thousandths of an inch, and you're going to see, maybe occasionally you see like 50 millionths or something like that. But in general, it's going to be somewhere in that range, and that's what you're going to put on your print. You don't want to get there the first day and put some ridiculously tight tolerance or something that's not normal on the print, because then it's going to probably tip people off that you don't really understand what's going on here. So you need to understand the lay of the land, so to speak, for that. And also, if you find yourself in the position where you're told to, or you need to make drawings to make the tools, just use what you need to communicate, right? So the drawings and the models and everything, we said this other areas, it's just for communication. That's all it is, right? It's not a law of physics. So adhere to the standard as your company sees it, and make it so that it's, communicating clearly your intent. So that's how you're going to do it. Okay. And also, if you're in charge of making any sort of tooling and you're having it done in-house, you're going to want to try to understand as best you can what standard tooling you have available to make the tools. So if you have to buy a lot of strange equipment or expensive or rare things that are hard to acquire, then it's going to take a lot longer and cost more. If you can kind of figure out, okay, what tools do we have available, and you can use those tools to make what you have or make what you need, then it's gonna be a lot faster and go a lot easier for you. So you gotta think of that while you're making your tools. And also, make sure again we cover this in CAD classes in our drafting classes, but pay attention to this when you're doing tooling drawings. Things like your surface roughness and your tolerances and all this should be on your print. And if your drawing is not clear, make sure you do use notes. It's okay to use notes whenever they seem warranted. So I don't want to say use too many notes, but it's better to be clear than leave things to chance, because especially when it comes to something like tooling, I can assure you that if you leave it to chance, it's almost never going to work out randomly in your favor. It's usually not going to work. So make sure you are clear with what it is you're trying to show. So whoever's making the part, whether it's another engineer, maybe you're the designer, and then you give it to the internal manufacturing engineers who are making the tooling, and then maybe they work with the technicians who are running the machines. It makes their job a lot easier. So you're going to want to think in that way. If I pick this up and I don't know all the ins and outs, can I get there with what I'm giving them? That's really important. And then you're also going to want to, again, this is kind of repeating, but use realistic tolerances. And that, depends on what you're doing. If you work at a company that's making gauges, you're going to have different tolerances than a company who's making, parts to hold, something that's really, I don't know, if you're making Nerf guns or something like that, maybe the tolerances in some areas are really tight. Actually, probably some of those things snap together with really tight tolerances. I know Legos are extraordinarily tight tolerances, believe it or not. But, some other things like that, if they're not critical, they're not going to be so tight tolerance. So you need to really understand what matters where. And this is a general thing, but it's general, but it's specific in that make sure you specify what you need. So sometimes on a print, if it's supposed to be an entire data package, you're going to have to include your bill of material and your notes, and the tool makers or whoever are actually making your tools. Probably if you're doing the drawings and the design, you're probably not also making your tools. Someone else is probably making them for you. Remember, they're your friend. They're there to make the parts, and it's really easy to leave out information or overlook things and cause issues there. So the more clear information you have in a way that people are used to seeing, the better off you are. And that's just a general rule I would adhere to. And then when you lay out a tool, so if you have some sort of tool, some fixture that you're going to make some part on, so you're the company that makes the part, and you also make you make your own part, you sell it to whoever buys it, and then you're making all your fixturing and everything. You need to make sure that you lay it out so that you're really indicating all your locating requirements. And that's something that, from your GD&T class and your CAD class, you'll learn. And as you start to make stuff, you'll understand that that's super important. So make sure that you do that as well. And to go along with that, you're going to want to indicate all your clamping points on a part. So, if you have some part and you're, we can just generically, this is just very generic here, and you have some sort of part here, some fixture, and then you have some sort of part, and let's say the part is like this, and you're going to clamp on the part. You might want to clamp here and here. If you clamp here and you put pressure on the part may like bow like this or something like that. And this is an exaggeration, but that kind of thing can happen. So again, don't leave anything to chance. You want to make sure that you're really clear with everything that you're doing on your tool. So if you find yourself in a tool design situation where you're making a fixture or whatever, these are the things that are going to become really, really important to you really quickly. And then another important concept, your book points this out, and I always point this out because it's really, really important to think about, but you should always have an idea of safety first. So you don't want to mess with safety. If you are making a tool or a fixture that's supposed to hold a part, that's supposed to resist cutting forces, it needs to be able to stay intact and withstand the rigors of whatever it's going to see without failing in a way that someone could get hurt on. And you need to build your safety into the process. So if you're going to have a part in a fixture, you don't want that part coming out. It needs to be held into the fixture properly. And if possible, the operator needs to be, even when they're loading and unloading it, you need to be thinking about how they're going to reach into the machine or out of the machine so they don't, get hurt. And in general, it's worth mentioning though, machines have interlocks on them, and do not mess with safety interlocks. So if you ever find yourself in a situation at work where you are having to defeat safety interlocks in a machine that are designed by the manufacturer or specified by your company to be there, you're probably doing it wrong. So, if you ever find yourself in that situation, you should default to, hey, we shouldn't be doing this. If you're defeating interlocks in a machine, then just stop right there. So you should probably just, call somebody or do something to make sure that situation is not left on. And if you see it and you work there, I would say you're obligated to, speak up, and you'll always, be fine if something's going on and you see a safety violation, and it is a true violation. You can't say this is unsafe, or you shouldn't say this is unsafe just to get out of doing work or something ridiculous like that. But if it truly is unsafe and you say it's unsafe, you're not going to get in trouble. And if you are working at a kind of company where you would get in trouble for that, just quit and get a job somewhere else and let them do their own thing. You don't want to work there. So, you need to always be safe. Safety is number one. And then you should always use guarding if the work can't be completely contained. So that usually pertains to some of the, CNC type machines are guarded. There are different machine tools in shops where extra guarding may be necessary. Maybe some sort of like grinders or knee mills or that sort of thing, where you might want to set up some extra guarding. But this usually comes about when you're working with, or not always, but oftentimes if you're working with robots and presses and that sort of thing. Sometimes they're designed to work in kind of an open environment, but the area where they're in should be guarded so that you cannot get into that area or get injured. And you should always wear PPE when appropriate. Make sure that that's a priority for you, because you really don't want to get injured at work. And also, don't do this here, and I'll let you click on that link and you can watch that video on your own. It's a pretty interesting video. Don't do that. So that's not what the robots are for. They're really expensive, and the robot will squish you and not even realize what's happening. And we'll talk about that more later in the semester. But anyway, this is general tool design. This covers the first chapter in your book, and you should at this point have a pretty good idea between this and your book and some of the other supplemental materials I'll have of kind of what we're going to be getting into for the rest of the semester. So thank you.